Hi guys, we're going to be talking about in section 12.4 Convergent and Divergent series. Here is our vocabularies. I'm not going to actually write some notes for right now, but here are the words that I want you to be looking forward to defining for yourself as we go through some of this work today. The word diverge or divergent, we'll talk about that really soon. Ratio test and comparison test. And really today we're going to think about whether or not we have a series that converges to a specific number or diverges, is just out of bounds, it doesn't have a limit. And so diverge means that it doesn't have a limit, it's out of bounds. Ratio test and a comparison test are two tests that we're going to use to determine whether a series converges or diverges. So let's go ahead and get started with example 1, convergent or divergent series. So if an infinite series has a sum or a limit, the series is convergent. If a series is not convergent, it is divergent. So let's keep that in mind as we look at example 1. We're going to determine whether each arithmetic or geometric series is convergent or divergent. Well, here it looks like we're dealing with a geometric series. You can see 1/2 and then negative 1/2 seems like it's multiplied by a negative 1/2 again, and then we get a positive 1/4, and if we multiply that by negative 1/2 we get a negative 1/8. And if you want to confirm, you can take any two consecutive values, 1/16 divided by 1/negative 1/8, and you can see that the common ratio for this geometric series is negative 1/2. And if you remember from the last section, as long as that common ratio, the absolute value of that common ratio is less than 1, we know that this particular series has a sum. We know that there is a sum value, there's a limit, there's a sum, there's a stopping point, there's a place that we're approaching a certain value. And so with that in mind, we can say that this series is convergent. It's going to converge on a number. Here we have another geometric series, and we can tell that by looking at the ratio 4/2, 8/4, 16/8. All of those tells us that the common ratio is 2. And since the common ratio is 2, which is not within the boundary lines of what we need that the absolute value of the common ratio is less than 1, and that's not what we have, we can say for certain that this is a divergent series. This is a divergent series. Over here we have, oh look at that, we're just going to keep adding something on. This looks like an arithmetic sequence. Let's see if that makes sense. What are we adding on, 1.5 or adding a negative 1.5? That looks like what we're doing, adding a negative 1.5. And so when we have an arithmetic sequence, we always know that these guys will never converge. They're always divergent. And that's what we know from this one, so from this example 1. Now, the thing is, example 1 only dealt with arithmetic and geometric sequences. And so it's kind of easy to tell if all arithmetic sequences will never converge and geometric sequences will converge as long as we have this common ratio thing. That's fine. But what happens when we're not dealing with that type of sequence? So let's take a look at the ratio test. So let a sub n and a sub n plus 1 represent two consecutive terms in a series of positive terms. Now this is only for a series of positive terms. So suppose that a sub n plus 1 over a sub n exists, and that r, the limit of that exists, and that r is the limit of that ratio. The series is convergent if r is less than 1, and divergent if r is greater than 1. Now, if r equals to 1, the test provides no information, so it's inconclusive. So the hard thing is, like, how do you find this? Do you really just put the numbers on top of each other? What we want to do is create an equation or an expression that kind of relates the numerator and denominator relationship. So we see 1/2, 2/4, 3/8, 4/16. These numbers are going up sequentially. These numbers look like powers of 2. So this looks like 2 to the 1 and 2 to the 2 and 2 to the 3 and 2 to the 4. So given that, if we call this number at the top n and we call this number in the denominator 2 to the n, we see we have a relationship that we're talking about here. We can mimic this relationship here. So if we kept going and had 2 to the 5th power, that would be 2 to the 5th at the bottom, which would be 32, and then at the top it would be 5, and that seems to be conclusive. So what do we have to do? How do we use this test? So what we're looking to figure out is what is the limit as n approaches infinity of this situation here of a sub n plus 1 over a sub n. So what's a sub n? A sub n, this term is going to be a sub n, this term is going to be n over 2 to the n power. And then a sub n plus 1 is going to be n plus 1 over 2 to the n plus 1 power. So let's do some simplifying of this. When we multiply or divide fractions, we need to multiply by the reciprocal. So let's take a look. We've got n plus 1 over 2n plus 1. That's the numerator. And I'm going to multiply it by 2 over n over 2 over the n power, right? Just to the n. And so what does that equal? Let's simplify this. So 2 to the n over 2 to the n plus 1 is really just 1/2. You guys see that? And then over here, we've got n plus 1 over n. So do you remember how we talked about finding the limit? And remember, all of this, we're still trying to find the limit as n approaches infinity. So if I look here, 1/2 is just a part of the picture. I'm going to have to multiply my answer by 1/2. But as I look at this, notice that the degree of the numerator and the degree of the denominator are equivalent. So really what I'm focusing on is the ratio of the lead coefficient, which is 1 over 1. So 1 over 1, this whole thing, as n gets bigger and bigger, is just going to go to 1. This is going to be 1/2. So 1 times 1/2, let me drum roll it for us. As n goes to infinity, this ratio that we have, that we created, which is really just an plus 1 over a sub n, that's equal to 1/2, meaning one term, the second term, over the original term, the first term, or the term before it. Is that all right? So since, let's go back, what does our law tell us? It says, hey, if we figure this out, it's equal to some r, then the series is convergent if r is less than 1, and we see that our r value is less than 1, that is the value of the limit, and therefore we are going to say that this is convergent. All right, remember this test is used when we're dealing with two consecutive terms of the positive terms of a series. So let's go ahead and look at this situation again too. So what could be the way that we could express these terms in this sequence or this series? If we continue with the idea that that's equal to, like, the top number is equal to n, then the bottom number looks like it's going to be equal to n plus 1 more. So here, if this is n plus 1, this is going to be n plus 2 at the bottom, and it looks like that's going to be consistent. So whatever the numerator is, the denominator is 1 more than that. So a sub n is equal to n over n plus 1. So if that's a sub n plus 1 has to be n plus 1 over n plus 1 plus 1. Yeah? So we're going to find the ratio of this with a sub n plus 1 at the top and a sub n at the bottom. Let's do that. So n plus 1 over n plus 2 over, that's a sub n plus 1, over n plus 1. Wow, I feel like I'm saying this over and over again. I think it sounds crazy, but hopefully it's making sense to you all. N plus 1 over n plus 2, I'm just coming right down here. I'm going to multiply by the denominator, the reciprocal of the denominator, which is what we do when we divide. So we end up with this. So now I've got n plus 1 times n plus 1 over n plus 2 times n. If I were to multiply this all together, again, I'm looking for the limit as n approaches infinity. If I were to multiply all this together, I'd get n squared plus 2n plus 1 at the top. At the bottom, I get n squared plus 2n. Do you guys know what the limit would be here as n approaches infinity? Remember what we said about the degree of the numerator and the degree of the denominator? since the degree of the numerator and the degree of the denominator are the same, we're going to go with the lead coefficient. And so the lead coefficient is 1 over 1. Therefore, this value that we were looking for, r, as it's called up here, is equal to 1. And so we realize that this test does not provide any information because this value is equal to 1. So over here, we're confident that it's convergent. Here we have no information or inconclusive information from that test. All right, let's see if we could use the ratio test to determine whether this series is convergent or divergent. So let's look at it and let's see if we could rewrite it in a way that would be interesting. So this looks like 1 over n factorial. That's not how your text does it, but I think we can do it. So you remember 1 factorial is equal to 1. 2 factorial is equal to 2 times 1. 3 factorial is equal to 3 times 2 times 1. And this exclamation point is called factorial. Well, I'm going to use that in this problem. So if you're not familiar with it, see if you can kind of think through what we're talking about here. N factorial would be n times n minus 1 times n minus 2 dot 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 all the way down to 1. So let's think about how I can write this. So whatever n is, it's the a sub n value. The first value is going to be n, or really 1 actually. It's always 1, so I don't have to do that. 1 over n factorial. That's what I'm looking at here. So if a is 1, that's 1 over 1 factorial, which is 1. If a is 2, that's 1 over 2 factorial, which is that. So I'm going to use that. I think this is going to be good. And so if that's 1 over n factorial, then a sub n plus 1 is going to be 1 over n plus 1 factorial. And so now we're going to divide these. 1 over n plus 1 factorial over 1 over n factorial. We're looking to find the limit as n approaches infinity. So that's what we're trying to do here. And so if we do that, we're going to again try to simplify the whole thing. As n approaches infinity, we're going to use 1 over n factorial. Hold on. 1 over n plus 1 factorial. And we're going to multiply that by the reciprocal of n factorial over 1. And so what happens is these guys cancel out. You get n factorial over n plus 1 factorial. And if you think about what this means, this is n times all the numbers less than it. This is n plus 1 times all the numbers less than it. So really, when I reduce them, I'm going to get 1 over n plus 1, meaning all the values n times the next number lower times the next number all the way down to 1 is present in the denominator. The only value that's here in the denominator that's not in the numerator is n plus 1. And so we're left with 1 over n plus 1. What is, as n goes to infinity, where does this go? Well, as the denominator has a higher degree than the numerator, then we know that this thing is going to 0. And so in this case, using the ratio test to determine whether this series is convergent or divergent, since r is less than 1 in this case, 0 is less than 1, we can say that this series doesn't diverge, but it converges. It is convergent. There we go. All right, so here in example 4, we're going to determine whether this series is convergent or divergent. So we can try the rule that we had before. In this case, we can look at this as 1 over n is what a sub n is, because if a sub n is 2, it's 1 over 2, so forth and so on. And so if we were to do that, a sub n plus 1 over a sub n, and we're trying to find the limit as n approaches infinity, let's go ahead and simplify a bit. Then we get 1 over n plus 1, right, over 1 over n. And then what we'll do is we will write this as 1 over n plus 1 times n over 1, which is n over n plus 1. As we consider n going to infinity, That means getting super large, super large. Remember that the degree of the numerator and denominator are the same here. So we are thinking about the coefficient. We've got 1 over 1. And what that's going to lead us to is 1. And remember, this is the inconclusive form. So what our text offers to us is not really a test, but kind of like a logical thought process. Okay, so that's inconclusive. But what if we were to take these numbers and say, okay, that's 1 and that's 1/2. And if I were to add the next numbers, like 1/3 plus 1/4, clearly this is bigger than 1/2 because I know 1/4 plus 1/4 is 1/2 and 1/3 is bigger than 1/4. So this is bigger than a half. So I know that this is greater than a half. You guys with me? This is greater, wrong symbol. This is greater than 1/2. Like this is, no, I guess it was the right symbol. Anyway, so this thing here is bigger than 1/2. And then I can kind of continue with this grouping phenomenon that I'm doing. Remember, this goes on forever. And so 1/5 plus 1/6 plus 1/7 plus 1/8. Well, wait a minute. That has to be greater than 1/2 too, because if this were 1/8 plus 1/8 plus 1/8 plus 1/8, that would all be 4/8, which is 1/2. And so this is greater. This thing here is greater than 1/2. Let me get my symbols in order. Greater than 1/2. So already I got 1, 2. And all I got to do is keep doing this. Now I know my grouping is getting bigger and bigger, but 9, no, 1/9 is what's next. I can count, I promise. Plus 1/10 plus 1/11 plus 1/12. And if I do this 8 times, I'm going to get up to 1/16. And if I were to add 8 1/16, that would be 1/2. But since these are bigger than 1/16, I know that this is greater than 1/2. Now I've got all of eternity to do this. So I can just keep grouping larger and larger groups of fractions such that I always am sure that I'm adding more than 1/2. And in this way, we can quote unquote prove that this series is divergent because it is not, I know it feels like it is, but it is not actually going to a number. I mean, we're adding a little bit more on every time, but when we add a little bit more on, if we do that twice, we're always going to get one more, and we can do this forever. So this is a divergent series. I don't know if that's as satisfying as the other ones. If it fits the rule, it feels better, but hopefully that made sense. Let's go ahead and look at the last example we're going to talk about, which is example 5. A series of positive terms is convergent if, for n greater than 1, each term of the series is equal to or less than the value of a corresponding term of some convergent series. So if I had a series, this is what this part is saying, if I had a series such that each of the terms are less than these terms here that we're talking about in this series, then since this is convergent, then this would be convergent, this first situation. The second situation says a series of positive terms is divergent for all n values greater than 1 if each term of the series is equal to or greater than the value of the corresponding terms for a divergent series. So it really is going to be nice for us to hold on to what a harmonic series is and the fact that it is divergent, and this series here, which we know to be convergent. Let's use that for example 5. So here we're going to use the comparison test to determine whether the following series are convergent or divergent. And what I'm going to do is I'm going to rewrite those two series that we know something about. All right, so we have those divergent and convergent examples above, and so let's consider what's going on here. If this is a sub 1 and we see that all the numerator is 4, we can say that a sub n is equal to 4 over something. Let's see, what would I do to 1 to get 5, and then do to 2 to get 7, and do to 3, because this would be a sub 3 to get 9. And so when I consider it, it looks like I'm taking the n term, multiplying it by 2, and then adding 3. 2 times 2 is 4, plus 3 is 7. 2 times 3 is 6, plus 3 is 9. 2 times 1 is 2, plus 3 is 5. So we get 2n plus 3. And so now if this is the expression that I'm using for a sub n, I can now compare it to this expression for a sub n in this particular example. So if I'm looking at this example, a sub n is equal to 1 over n. And what's the relationship between these two? Is there a relationship? Can I talk about a strict relationship between 4 over 2n plus 3 and 1 over n. And again, we're dealing with n as positive values. Well, I'm hoping you guys see that 4 over 2n plus 3 is always going to be greater than 1 over n. So 1 over n is less than 4 over 2n plus 3. What do we learn up here with the comparison test? It says if you have a series of positive terms in its divergent, we know that this is the divergent one, for n greater than 1, each term of the series is equal to or greater than the value of the corresponding term of the divergent series of a positive terms. I know I gobbled that and just reading it, but I hope you see that because this value is always bigger than this value, if this diverges, this will diverge as well. Therefore, we have a divergent series on our hands in this case. Let's try this guy. So in this case, we have 1 over, what would that be? 1 over n to the second power. This will be, 1 over n to the second power, 1 over, let me think about this. Not 1 over n to the second power. Let's see. If n is 1, what would I do with 1 here? It looks like 1 over 2n minus 1 to the second power. Let's see. So if I had 2 times 2 is 4. 4 minus 1 is 3, 3 squared. If I have, this is a sub 1, this is a sub 2, this is a sub 3. So n is 3, 3, 2 times 3 is 6, 6 minus 1 is 5, and 5 squared. So I have 1 over 2n minus 1 to the second power. And what we're going to be comparing this to is this over here, this convergent series, which we know is 1 over some number n to a power that is greater than or equal to 1. So I know that, let's say if I had 1 over n squared, let's say, that would fit this convergent series situation. And now the question is 1 over n squared, is that going to be bigger than or less than? How are they going to be compared? Well, remember, the larger my denominator is, the smaller the number. So clearly this guy is smaller than 1 over n squared. And just like our information told us, hey, if we have a series such that for each n greater than 1, each term is equal to or less than the value of a corresponding convergent series, then we know that that thing converges. And so from this relationship here with a known convergent series, we know that this is also convergent as well. All right. With that in mind, I'm going to stop here. I'm going to ask you to, take a moment, review, look at the information, make sure it makes sense, talk to me if it doesn't, and get started trying some problems to really see if you can solidify that understanding. All right, take it easy. I look forward to talking to you soon. Bye-bye.